Okay. So, hi, everybody. My name is Robert Burke, and I'm here to give you a short guided, short guided walkthrough of the Apache Beam Go SDK. I work for Google, and currently they employ me to work on the Apache Beam Go SDK because of a internal data processing project. So that kind of skews a certain measure of the development of the SDK from myself and the previous original authors. But the goal has always been to make sure that it is usable everywhere else. In particular, that skew was batch processing, not stream processing. So I'm not going to be saying too many things about windowing in this particular talk. So why would you want to come to this particular talk rather than Tyler's awesome time series talk down in the other room? Well, in specific, I'm kind of focusing on the parts an SDK needs to do as part of the whole Beam portability ecosystem. Because every time I ask someone about how Python does it and how Java does it, none of them could really trace what the SDK side needs to do. They would immediately jump to how the runner needs to start orchestrating stuff, and it was hard for me to follow. And then when I was trying to do so for myself, following the Java and Python SDKs, Python's lack of types made it very hard to jump around the code effectively, and I have a hard time reading enterprise Java. What this talk is not going to cover is I'm not going to try and sell the use of Go to you, or specifically the use of the Go SDK. Language choice is incredibly subjective, and you're going to use what you want to use. And really, that's kind of the whole goal behind portability, is to make it so that everything is available, as that Beam is available to as many users as possible through the languages of their choice. Currently, Java, Python, and Go. So if you want to know more about Go specifically, I definitely recommend going to Hacker News and seeing the opinions there. Moving along, there is the secret hope that because of portability that you all go off and make your own SDKs with other languages. Could be fun. And I'm definitely not going to teach you Go here, because that is a workshop in and of itself. But here's a bunch of resources for getting to Go, or getting around to learning Go. With that said, who here actually knows Go? Raise your hand. Okay. So I will explain as much as I can, or as much as is necessary, but Go as a rule, one of my favorite things about Go is that it's a fairly readable language, so you should be able to follow along nevertheless. As a quick little fun bit, this URL here, and hold on, goes to a demo on something called the Go Playground. Oh. Which I'm going to go briefly jump over to that, because really, So this here's the Go Playground. It's one of those resources that the Go team provides so that you can literally try out Go in your web browser without actually installing Go or anything. You've got a full text editor, which is all up in here. You can format your code, you can run it. And recently, it gained the ability to pull in arbitrary packages from GitHub. So you can try out any Go package that is available on the internet and just run it in your browser. Now, it's a sandboxed environment, so timestamps aren't implemented, like time is not properly implemented, and you don't have access to network. But what I did here was import the Apache Beam SDKs and the Go direct runner to actually just do a small bit of word count. So if you haven't seen the Go SDK before, this is what it looks like. It looks in my opinion, it looks relatively close to how you'd write the either regular Go code, and you can find the matching parts for the Beam model. It takes actually a few minutes to run this because it ends up downloading, sanitizing the packages and all that. So here's the execution output where it analyzes the pipeline, puts it all into its own little model representation, constructs the plan for how it works, and then because we're just running in a single bundle, single runner in a one single process, I'm just printing everything out. So you can see it does the word count for modern Major General right there. Anyways, I thought that was a fun little diversion. Let's go back to presenting. And since my slide notes went away. Okay, so that is, you can find that and play with that there if you so choose. A little bit about the Go SDK in general. It is the first purely portable Beam SDK. That means it doesn't have any legacy runner support at all. So without portability, there would be no Go SDK. But this means that it's definitely currently experimental, and I'll get into more details why later. As I mentioned earlier, it was initially developed by Google, internal to Google to handle particular batch use cases, and then externalized to the main Beam repo. Yeah, that's all I've got to say about that. So let's just dive right in. Specifically, what an SDK needs to get done compared to the rest of the runner stuff is, you might have been able to pick this up from the previous talks at the summit, but two main things. You need to be able to construct your pipelines, and then you need to be able to execute the fragments of pipelines that the runners send back. So now with that, we have, let's introduce like the main player here. So this little guy is just going to represent your pipeline, and he needs, like any kind of a video game adventurer, he needs the right equipment in order to solve his quest. His quest is to process your data. But fortunately for him, compared to a lot of video games, he doesn't pick up everything along the way. Most of it's provided right away in the initial Beam package. So all the main tools that you can use to construct your data pipeline are all in the main user-facing package. The actual import string is fairly long, so you can see it at the top there, github.com/apache/beam/sdks/go/package beam. And then everything else comes from the Beam root that it will reveal as this talk goes on. So Beam model, I'm not going to explain what the Beam model is. I'm just going to dive right into showing how the SDK looks how the SDK looks. The main package provides all the particular basics. You can create your new pipelines. You can invoke your pardoos, get your CoGroupByKeys, combines, flattens, so on and so forth. Everything that is part of the Beam model will end up hanging from this package in various convenience functions to construct your pipeline. Pardoos, P collections and elements. So P collections and elements, they can be any arbitrary Go type. From anything from the actual, or from renamed Go types, where you just are type segregating it with an underlying primitive type, to structs with various fields, or even more advanced structs with sub-definitions. The Go SDK will by default and treat everything by default as being coded by JSON, which is very convenient for debugging, less convenient for performance, but we'll get to that later. So anything that is JSON encodable will be perfectly usable with the Go SDK. There's currently, if you're a fan of protocol buffers, there's currently a mechanism to use protocol buffers and its encoding strategy instead, which provides some measure of compatibility when cross-language IOs end up being supported. Moving along, pardoos and DoFns. In the Go SDK, DoFns can be one of two things, really. Generic or regular Go functions, so any ordinary Go function with its plain returns, or it could be what we call a structural DoFn, which has access to the bundle lifecycle. notably process element, but also includes any one-time setup or teardown, or any start bundle or finish bundle methods. From there, you can also take in any particular, this is where I wish I had a laser pointer, but you're not limited to just the single in, single out returns. You can also have emitter functions in order to emit arbitrary numbers of output, or amount of output. And you can also see how you use the particular, use the construction functions to add things to your pipeline there. The little s parameter is something that you'll see a lot in these next few slides. It is representing the pipeline scope. It's basically saying at what layer or what composite level you're hanging these P transforms off of. And those the Pardo functions and any of the other major pipeline construction functions tend to return the P collections out, which then get assigned to variables as normal. This is functionally because so you might, for the handful of you who know Go, you might be confused why we're using some string methods or some arbitrarily named magic strings in order to do the pipeline lifecycle. This is because the authors of the Go SDK wanted to make sure that you could use your Go types in a more natural way, as opposed to forcing everything to adhere to some specific interface ahead of time. So what this diagram is supposed to indicate is the rough regular expression that your process element method can take in. You can take in a regular Go context. You can then take in the element's event time or windows, the actual input, which can be a regular input or the implicit KV pair, the series of side inputs, any arbitrary emitters for side outputs, and then same thing, you can do the event time, return an event time if you wanted to rewrite the event time, your standard primary output, and because this is Go, the Go error type. And it conventionally must be in this order. The system actually requires it and enforces that. Side inputs are done via additional, as indicated on this slide here, are possible. They come right after the input in your parameters and right before the output emitters, if any. And they can take a variety of forms. They can take. We have the facility to, because we don't have generics in Go, but we do have some measure of strict typing. It's possible the Go SDK uses actual regular Go functions to handle its emitters and its side inputs. You can see up at the top there, bounds iter is using pointers and a function that returns a Boolean to do an iterator, so you can iterate over the data from your side input in an efficient manner. But there are some additional conveniences that we've added to the SDK as well. Instead of just having a function that you manually iterate over, if you know you absolutely need everything, you can have it return a slice, which is a variable length array, a variable length list of elements that are strongly typed. And the SDK will provide all the elements to you that way instead. Or if you know you only have a singleton element as a side input, you can just ask for a singleton element. And if it's not a singleton P collection, then it will fail at runtime. So at least you will not be producing bad data. I forgot to adjust that arrow. Unfortunately, it's a little covered by the arrow, but when you're invoking your additional Pardo, you can declare your side inputs by providing additional options to the construction function, indicating that you have these side inputs. This will all get type checked at pipeline construction time, that the bounds, that the P collection that you're passing in as a side input matches the DoFn that you are passing it into, and otherwise things are in positional order. So, for example, with the outputs of this one, you'll note that for the top level signature there, we have the high, mid, and low emitter functions. and no actual return types for these DoFns. Those are returned in that order as P collections from the construction function, and you can see that right there. Moving along, CoGroupByKey, because everyone's favorite thing to do these days is joining things together. Also leverages, they also leverage the iterators. They're strictly required to be the iterators. And when a CoGroupByKey, so the system analyzes your DoFn and determines it's a P-transform by noting it has these particular iterator types. And it can take in any arbitrary number of iterators, and the system will again type check to make sure you're passing in the appropriate inputs into the CoGroupByKey. And it's actually a two-part system here, because the CoGroupByKey is its own node. It just returns a P collection of the CoGroupByKey type. So anything that you've got in the same key space, you can then join together if you've got multiple collections with that key space, or just even having a single one, even if that's all you've got, and then it's a regular group by key. Combines extend further the same kind of thing with the DoFns. They have access, these ones are specifically designed to take advantage of combiner lifting. So instead of having your own instead of needing to implement your own mapper-side combines in some awkward way, the combine operation has a CoGroupByKey within it, and the system will properly lift the add input operations and push down the merge accumulators operations so that mapper-side combines can be done. Or pre-shuffle combines. There's so many words. There's so many terms for those things. But otherwise, you can use your own types, just like any other combine. You can have a distinct input type, accumulator type, and output type, and convert between them as necessary. All these except for the merge accumulators and the process element method from the DoFns. The other methods are totally optional. So overall, although I showed you the little demo, this is another view of the pipeline, and I'm going to represent our hero for the rest of this journey through the SDK. We're not really going to be looking at this code in particular. It's just to give you the complete picture. When you're invoking a pipeline, you just preferably do it at the beginning of your main function. Somewhere near the beginning of your main, you should be calling beam.init, and I'll get to why at a later point in time. Construct your pipeline, and then you can run your pipeline in whatever available runners. The BeamX package there for BeamX run is a convenience selector to be able to select between any runners that are already installed. But for the most part, if you're running against Flink or Spark, you'll just need to use the universal runner where you submit things to the job server, and that's all standard command line parameters. But this isn't a workshop, so I'm not showing you all that. So one thing that I noticed while I was going through this talk is that when you're writing an SDK, you need to adhere to not just the idioms of your language, but also the idioms of Beam. So I thought this was just a good image that kind of represented that. Is it a duck? Is it a rabbit? Is it Beam? Is it idiomatic Beam? Is it idiomatic Go? And you have to strike a balance when you're writing your SDK, because authors from a given language will expect certain ways of doing things, and if you don't adhere to those patterns and idioms, they're not going to enjoy writing in your system as much. For one example, it's not very common in Go to use chaining and to apply chaining. While there's no reason why the Go SDK couldn't do that, it was not implemented in the base SDK. It can totally be added later on or contributed by one of you. So now that we've figured out our user pipeline, let's see what it takes to actually get it over to the data processing step. So in this next bit, there's two kind of packages that are involved. the core graph package, which retains the internal representation that the SDK uses to represent your pipeline. It segregates it puts the P collections as multi-edges and the P transforms as nodes, and make sure that everything wires together. This also handles the particular staging of composites with the scope object I mentioned earlier. P transforms, functionally free, usually via your pardoos, are analyzed and type checked in order to figure out what P collection they represent. And then when everything is getting hooked together, it checks to make sure that all the DoFns are receiving the appropriate input from their parent P collections. The core util reflectx package, which I will just abbreviate as reflectx, is what does additional wrapping and convenience wrapping for the DoFns so that we can invoke them later on. We'll cover that more when we get to the execution stage. Throughout a recent line code count of the Beam repo indicated that there's nearly 100,000 lines of the Go SDK, and we're not covering nearly that much. I would say about 40% of that is generated code that will probably get deleted. So the SDK is actually relatively small, and there's only 20 odd packages within the SDK itself. We're only going to be covering a handful of them in our little map here, but the ones that we're not really covering generally are these X packages. So if you're looking at the code and you see the X packages, the best way to think about those is that they are the ones that kind of do additional operations on top of those elements. So funcx operates on Go funcs, the term for Go functions. Typex operates on types, so on and so forth. Reflectx operates on the reflection parameters. And the other reason for separating some of these operations out is so that they can have a cleaner dependency graph. Otherwise, if they were included in the main packages, it would not be able to there would be cycles and everything would end up in one package, and nobody wants that. As a rule, users aren't necessarily going to be using any of these directly. They're largely just for utilities for SDK-side developers, or Go SDK developers for changing and modifying the SDK. Moving along, P collections are represented largely by, or handled largely by the FullType class coming from core/typex. The FullType class is the notional representation of your full P collection type. So if you have because Go does not have generics or duck typing, there's no way for Go to specifically say KV something or other without having some kind of indirection here. Like in Java, there is an explicit KV type that you put your pairs of elements into. That's a little awkward in Go, and you would lose the full strong typing information if we did that. So in order to maintain that, we have this carrier class to hold the P collection, the type of a P collection. So there's a couple different things here. Class is kind of notional on whether it is a concrete type, as in it's one of the actual Go base types or elements that you're constructing things with. So any of your user types tend to be concrete. They could be a composite type, like KVs or CoGroupByKeys. And the reflect type, it ends up pointing to either the top level, whatever the top level type is. So reflect.type is part of the Go standard libraries reflection package, and you can think of it as a java.class object, if you're familiar with Java. And components allow us to have the full nested tree of CoGroupByKeys with KV types and so on and so forth. So with that, portability is almost in sight. We've got our pipeline, it's constructed, we know the types of everything, we know how our DoFns are hooking together. But the thing is, the Portability API requires one more thing for us to get it working, and that is serialization. So another thing that Go does not actually have is built-in support for serializing your types or your functions. That's just not a thing that's included in the language. The Go authors did so because having that kind of support, especially when things can be invoked reflectively, means you can't do a lot of convenient binary pruning. You can't elide things that aren't being used, which leads to larger binaries and binary bloat. So they opted for the approach that does not lead to that, which means that we need to look for alternatives for serializing our types and DoFns. The packages that retain that kind of information or operate on that kind of information in the SDK are core/runtime and core/runtime graphx. We end up serializing types and functions. Like I said, it's not built into Go, via one of two ways. For types, we either actually do a full reflective recursive search through its type or its actual struct types and serialize that in a protocol buffer, which we've mapped every Go type to, and then we serialize that. On the other side of the river, we end up using the reflect package to completely synthetically recreate a type if that approach is used. Alternatively, if you register your type in a package init time using one of the Beam methods I will show in the next slide, we then just have the reflect type variable, and we can just use so directly, which is much more concise a representation, especially for complex types, and also leads to certain performance benefits. For functions, there is no way to look up a function based on its symbol in the Go SDK. So if you don't register your functions, what ends up happening is we fake it and then look things up in the binary's symbol table, debug symbol table, which, as you can imagine, is not the best way to do things and is incredibly brittle. It works, but it's not guaranteed to work forever. It is largely just convenient for initial running and not needing to deal with all this registration ahead of time. It lets you experiment more freely. That's basically what's happening, or what happened in the demo earlier with the anonymous functions. Similarly, we also provide a registration approach for functions, which is dramatically better, because then we don't need to look up pointers and cast things to the appropriate types via the symbol table. You can see how we register stuff. Functions, it's very straightforward. You take the function reference and just toss it in there. And then that way, when the binary comes back in worker mode, it can just get at it. And for types need to be done both for structural DoFns or combined funds, as well as any of the data types that you're using in your pipeline. Otherwise, this makes the graph representation much larger. So at this point, we jump into the river of portability and send things off to the runner. And this is just a cute gopher with an inner tube. At this point, the metaphor kind of loses its sway. I think at this point, the runner is more of a boat helping you get down the river, but that doesn't quite work out either way. The runner does the things the runners do, which you've heard about at length from Spark and Flink folks earlier today and yesterday. So we'll just assume they did all of that. And we're going to cross to the other side of the river into the worker harness. So many slides ago, I mentioned beam.init. That is, you want to call that as early in your binary as possible, possibly short or just before you do flag processing or similar, so that when the runner ends up spinning up your binary again as part of a worker, it can use that to switch into worker mode. And spin up the SDK harness for Go. The SDK harness is conveniently located in Beam core runtime harness. and contains all the code. This is where the main connections, gRPC connections for the Portability API are made, and it connects to the runner side of the worker from there. And this is where it starts receiving bundles to be processed. So once it then pairs with the exec package to undo all the serialization work. This is also calling into the GraphX package to reconstruct and reify all the types and pardoes that it needs to know about for executing your bundle. And so there we have a loose map of the main things that we need to process in order to process bundles. But now we've got the fun bit. How do we actually execute all your functions when we don't actually have generics or like actual explicit interfaces and all that? A little bit before. I'm getting ahead of myself. First, next up is actually passing around the data. So if you're reading things from shuffle or some kind of cross-language transform, data gets in between your pardoes and p-transforms within a bundle. We need a mechanism to pass the data around. So that purpose is currently served by the full value type for Go. This is it. Because the Go SDK deals with KVs as implicit values, we have elm1 and elm2 to handle the case where your main input is either just a plain element or a KV pair. And this also associates the timestamp in Windows with those elements. Following that, in order to process side inputs and iterators, we have this concept called, we have these interfaces called stream and restream. Restream, as you can see, is a very simple interface. It is able to construct streams. Part of the contract there is that whenever you call open, you're getting an exact copy of the stream that will start from the beginning. This is very useful when you're using side inputs as a reiterator as opposed to just an iterator. I didn't show a reiterator, but it's quite simply a function that returns an iterator function. And then you can call that, and it eventually indirects to the actual processes here. Streams can be closed so that we can cut off the data connection if necessary, but otherwise it will just return a set of full values to be read and then processed by things before they get passed to the user functions. In the exec package, we've changed most of the p-transforms or all the p-transforms are being implemented implemented these interfaces. For lack of better name, it got called unit, but you can see it represents the bundle lifecycle for the most part, where things are started up, things can be torn down, and start and bundle and finish bundle are done as well. Further, there's the element processor interface, which then executes things with the full values. Now is how we actually execute arbitrary functions. So the answer, of course, is just reflection. We use, by default, if you don't do anything else, we use the reflect package, and it's the reflect.values call method, which I've got the type signature up there. As you can see, to use the reflect package call, you need to convert all the inputs into reflect.values and pass them as a slice into the call, and then you receive all the outputs out as a slice of values. This means that whenever you're using reflection for the Go SDK, anytime you haven't done anything differently, which I'll get to in a second, you need to pay the overhead of converting everything to reflect.values. To provide us with options, the original author, or one of the original authors, Henning Rode, decided to indirect this mechanism with the reflectx package func mechanism. So I mentioned func on the map over there, but the interface is very simple. We have some way of referring to the function, the name, so for debugging purposes, the actual type signature of the function, and the a very similar interface to call to the call function from reflect, except it uses, pardon me, the empty interface values of, oh goodness, Go SDK, of Go. This allows us to use, I'll use type assertion instead, which I will explain in a second. So the reason why we'd want to have some kind of alternative for this is in this slide. Say we have just our struct with a method here. So this is just a random Go struct with its own little method. If you call the method directly, it's about 2 nanoseconds per call. This is with all the compiler support to optimize all the calling and all that. So that is like as low as we could possibly get. But we don't have that luxury because everything is indirect. If we're calling a method indirectly, so we take that method and then cast it through its own function signature. So it's, in this case, it's a function that just takes an int and returns an int. And do a bit of indirection so that the compiler can't help us. Calling that through that indirection mechanism is 187 nanoseconds per call. And then further, when we actually use reflection to do all of this, including all the time it takes to convert things to reflect.value and back again. So even with just the single parameter that's getting passed in here, that adds up to a microsecond. It's like, it adds up. So this is just a single fixed cost. And granted, these numbers will vary depending on the number of parameters you're passing in and taking out. But we probably don't want to do that so quick or so much. The generated thing is we have a way of getting actual performance out of this. I spent a couple months actually working on this where we can use code generation, and that gets it down to 45 nanoseconds a call. The code, when you generate it, looks like this. No one's ever supposed to look at this, ever. This is just the convenience thing of how it looks. But instead of synthetically creating all the emitter functions and iterators and callers using reflection, instead we just code generate them ahead of time, and they kind of look like this. As a benefit of doing all the static analysis, and since we already have everything, we can also do all the registrations for you. So generate your code instead, and you'd stop worrying about it. You can invoke the generator using lines like these, because Go has a built-in Go generate mechanism to invoke code, not at build time, but as part of a build process. In this case, you just name your identifiers, or DoFn identifiers, and it will do the static analysis on your package to get everything out. Unimplemented features in the SDK, since we're running, this is taking longer than I thought it would. So here's basically the state of the SDK. Batch works very well. We have all the basics for things working for Pardus, CoGroupByKeys, combines, and so forth. There is basic windowing support, although to my knowledge, I don't believe there's any tests for it yet. And it only works for fixed and sliding windows. Custom window functions aren't implemented because they are not yet implemented in the portability framework, and like I said earlier, Go SDK doesn't exist without portability. State and timers, I do believe, have portable representations, but they aren't implemented in the SDK yet. The big elephant in the room is, of course, IOs, and kind of why I keep saying that the SDK is experimental. While we can write our batch IOs using just reading things from a DoFn and then resharding and praying that the runner actually like shards and splits things and parallelizes it, that's not ideal. We're kind of waiting for cross-language transforms to be implemented properly, and then we can port that onto the Go side, or better yet, splittable DoFns. Splittable DoFns do have a portable representation, and someone I work with is already working on that. So take a picture of this slide if you want some more information on the Go SDK. I definitely recommend the RFC. And for anything else, Apache Beam, the Go SDK. The code is fairly readable, very easy to follow because there's all those types. All the Gophers, most of the Gophers you saw are from this GitHub repo, Ashley McNamara. wonderful. And the Go Gopher was designed by Rennie French. I have been Robert Burke. Thank you. And I don't know if I have time for questions. I don't think so. Yeah, sounds good. I'm going to just unplug here. Yeah. Why is generated code? Oh, yes.
So the question is why generated code has 10 times worse performance?
So this is where it's using a mechanism in Go to do things. Using the direct call would actually mean I'm passing an int directly in. With the generated code, instead we have indirected things through the empty interface type, which means we need to use a Go mechanism called type assertions to say, oh, this is actually an int, and then pass it directly into the function. So that those extra 43 nanoseconds are representing that.
But then you kind of have types during code generation, so you don't necessarily have to use interfaces.
We could, so a different version of the Go SDK could probably have been almost entirely code generated for a lot of speed, but then it would have been impossible to debug.
Thank you.
Any other questions? Okay, thank you very much. If you have anything, please come find me. I'm very visible.